Wait, where did that? Oh, I skipped this. We looked at an example about the Iowa Basic Test of Basic Skills. Had an average of 6.84 and a standard deviation of 1.55. You may want to know how unusual it is for somebody, a seventh grader, to score less than 3.74. Remember that in seventh grade, you're getting a score of 3.74. That means your basic skills are that of a third grader about 3/4 of the way through the school year. How unlikely is that? We can look at the normal density curve, but again, finding that area under the curve is difficult. It's exactly 2 standard deviations from the mean, but what is that probability? And that's what we're going to put in for our applet. So you're going to put in the in your phones, you're going to put a mean of 6.84 and a standard deviation of 1.55. Okay, so like I said, when we were calculating probabilities based on uniform distributions, it was as easy as base times height, right? Well, that doesn't work for a normal distribution because the base times height would give you a triangle, but the data, this is not a straight line along the curve, right? So it's not exactly, and the more farther we go along there, the triangle is not going to be straight. It's not going to estimate the area under that curve, right? So base times height doesn't work because that would be a rectangle. A triangle might work way down in the little pieces, but any bigger pieces isn't going to work. And if I wanted to know the area between two different, from here to here, well, that's definitely not a rectangle, right? So we have to have a way to calculate the area underneath the normal model, okay? And we're going to use the applet we just opened on our phone to do that. Okay, this data is from that value of 3.76. Okay, about what proportion of Gary, Indiana 7th graders have an ITBS vocabulary score between 5.29 and 8.39? That is, what percent of the area under the normal curve lies within 1 standard deviation of the mean? Our question is, what proportion of Gary, Indiana 7th graders have a score between 5.29 and 8.39, which is 1 standard deviation from the mean on both sides, right? So what did we get? 68.27%. So we expect approximately 68.27% of the 7th graders to be in that range, within 1 standard deviation of the mean. Okay. What about the students that are between 3.74 and 9.94? That's about 2 standard deviations of the mean. What percent of the 7th graders are within 2 standard deviations of the mean? Go ahead and plug those two numbers, the 3.74 and the 9.94, into the into the applet.
And so you're just using the applet?
We're going to use the applet to find those areas. Eventually, we'll learn how to use the calculator to do that, so you don't have to go into this applet on the computer.
So, is there a way that we have to learn how to do this without the applet?
Yes, we're going to learn how to use our calculator to do these calculations, so that you don't have to go in and no.
Is it just like how we use the calculator for like the stat stuff, like on the other quiz? Like, you know?
No, I mean, it's a little different for sure. But there's definitely like a command. You just put in what you need and it'll give you the answer out. All right, what did we get? What proportion is between 2 standard deviations from the mean?
95.45.
So about 95% of the 7th graders are expected to be between 2 standard deviations of the mean. And then can you find what percent we expect to be within 3 standard deviations of the mean? 2.19 and 11.49. 99.73?
Yes.
So 99.7% should be within 3 standard deviations of the mean. That's almost all of it, right?
Yeah.
Okay.
It's always going to be those same exact percentages every time.
Let's look at the distribution of IQ scores.
One standard deviation is always...
The mean of IQ scores is approximately, or the IQ scores are approximately normal with the mean of 100 and a standard deviation of 15. So go into the applet, change your mean and standard deviation from 100 to 15. 115 from your last ones. So we've adjusted.
So it'll be the same no matter the number, like no matter the value. It's just gonna be the same number.
Yeah, so even though we changed the mean and the standard deviation, we still got 68.37% between 1 standard deviation and the mean, right? Did you check the other ones? Check 2 standard deviations and 3 standard deviations. Are you gonna get the same numbers?
Oh, between 55 and 1.5, I still got 9.
I thought it was 2.7.
Oh yeah, it's all the same.
It might be. I'm just trying to do it from memory.
It is 2.7. So that's it's always gonna be like that.
It's always going to be like this. Now, we're going to readjust our app again. We're going to go to a standard normal distribution. What did we call the standardized score in the last section? The z-score. Okay, so this is the standard normal that uses z-scores. Change your mean to 0 and your standard deviation of 1. We're going to write down this summary for any normal distribution. The area under the curve within 1, 2, and 3 standard deviations of the mean is about 68, 95, 99.7. So here's our empirical rule. That summarization, that summary you wrote, is the empirical rule. So you need to write empirical rule. About 68% of the values fall within 1 standard deviation of the mean. About 95% of the values fall within 2 standard deviations of the mean. And about 99.7% of the values fall within 3 standard deviations of the mean. This is known as the empirical rule. In AP Stats, we call this the 68, 95, 99.7 rule. 68, 95, 99.7 rule. So that we can remember those numbers. Okay? But we also need to recognize that it's called the empirical rule. So take a second.
Can I take it?
There are many normal distributions. They all have properties in common. All normal distributions obey the empirical rule. Some people refer to this as, like I said, the 68, 95, 99.7 rule.
Wait, I have a question.
Yes.
Why do none of them have decimals except the last one?
Don't worry about it.
Because
Oh,
it's
no, I know they all have decimals, but like, why aren't they included?
because it's close enough to 68 to say 68%, but 99.7, it's like almost all the data. So we wanted to include that 0.7 because it's not 100% of the data. 100% of the data is not within 3 standard deviations of the mean. There's still 0.3% that's greater than or less than 3 standard deviations from the mean. So I don't know why they chose the round.
Do we have to write this down?
The only thing I would write from this slide is also known as 68, 95, 99.7 rule. 68.27, which rounds down to 68. If we remember these three numbers, we can quickly estimate proportions or percents of observations in a specified interval in a normal distribution. Okay, so the distribution of Iowa test of basic skills vocabulary scores for 7th grade students in Gary, Indiana, again, can be modeled with a mean of 6.84 and a standard deviation of 1.55. Use the empirical rule to answer the following questions. What percent of these students have a score less than 3.74? So we're going to draw this again. We're going to draw our normal model. In the middle is my mean, 6.84. Okay, you're going to need to draw this when we're doing the homework. Yes, draw this with me. We're going to add 1.55, right? 3 times, so 6.84 plus 1.55 makes this 8.39. Add 1.55, 9.94. Add 1.95, 11.8. Oops, sorry, I did. Yeah, yes. 11.49. And then we'll subtract 6.84 minus 1.55. We did this on the homework on the last section, right? Minus 1.55. 3.74 minus 1.55. 2.19. So this question, like in the one slide we looked at earlier, is asking, what is this area? What percent of 7th graders do we expect to be less than 2 standard deviations from the mean? Approximately. Eventually we'll work on getting an exact answer, but right now we just want to approximate. We know that 1 standard deviation is approximately 68%, and 2 standard deviations is approximately 95%.
Is that 11.49?
Yes. So we're interested in, oh dang it. What percent is this? So,
Will we put that in the?
what do we know? No, I don't want you to put it in there yet. We want to learn to do this without the calculator thing. The normal model, just like all probability distributions, adds to 1 or 100%. Okay, so the entire area equals 1 or 100%. Somewhere on my desk, yeah. It's right in front of my computers. Okay. Okay. Can we logically figure out what this percentage is going to be? The whole thing adds to 100, right? The middle 2 standard deviations is 95%.
20.
What percent does that leave in the tails?
15.
Wait, I have 95% is in the middle. How much is left? 5%. And they are divided evenly on each side, right?
So
2.5%.
I knew that.
Because 100 minus 95 is 5%, right?
Yeah.
But that is both this tail and this tail add to 5%. And this is a completely symmetrical distribution. So when I divide that by 2, I get 2.5.
Can I color out the inside as well?
Yes. So we have 2.5% of data will be above 2 standard deviations from the mean. That means it's pretty rare to be that far from the mean, right? It's rare for a 7th grader to have a score that's above 9.94, which basically means they're about 10th grade level while they're in 7th grade.
That's good.
Yeah, that would be really good, but it's rare. Only 2.5% of the time we expect that to happen.
And then some
Was that
kids
you?
are like,
Were you part of that 2.5%?
I don't know. I didn't grow up in Indiana. So I didn't take the Iowa test of basic skills. So, okay.
Wait,
So let's talk a little bit about yeah.
did the question ask about the 95%?
It asked what percent of students have a score less than 3.74. That's the red area we have colored in.
So if you wanted to know the 99.7 percentile, would you go all the way to the 2.19?
Yes.
Okay.
Yes.
Great.
Okay. Let's talk a little bit about these. We're not gonna draw this again. The next question is, hey, you're gonna have to use some thinking here.
all thinking's hard.
I'm gonna have you and the person sitting next to you try to figure this out.
Use your brain thought.
What is the area from 5.29 to 9.49? What do you think that area is going to be? You're going to have to use some subtraction skills to figure out what from here to here is. I meant to use a pen on that. What do we expect this to be?
Oh, between.
What do we expect it to be less than? Can you figure that out? Okay. What do we know? Once again,
You have no percent.
the whole thing is going to add to what? 100. So can I figure out how much is above 68%?
Would you subtract 100 from 68?
100 minus 68 gives me 32. Now that's on both sides, right? So the proportion, guys, you need to know this stuff. The proportion that's above one side, above 1 standard deviation on either side, is, got to divide that by 2, 16.
Why do you have to divide it by
Right?
12?
Because it's in both. When I say 68% minus 100, that's the whole thing. There's two sides to it, right? If I only want to know what's on this half, I have to divide it by 2. So 32% is left outside greater than or less than 1 standard deviation of the mean. That makes 16% above 1 standard deviation on the either side, right?
Okay.
And then I want to stop here at the 2 standard deviation mark, right?
Yes.
We already said how much is above that 2 standard deviations part. 2.5%, right? So I'm going to do the 16 minus 2.5 gives me 13.5%, right? And when I add that, so from here to here, I get 13.5. Some of you did it other ways, and that's okay. Some of you did it other ways, and that's okay. And when I add 13.5 to 68, we get 81.5.
Wait, you're adding it?
I'm adding it because I want from here, I want the whole pink area, here to here, plus here.
Wait, why are you subtracting?
That just looks like a lot of values to remember.
I'm not remembering anything. I'm just doing some calculations. Why am I subtracting what? Because I want it to stop at 1 standard deviation here. I want it to stop here, so anything above is a 2.5%. That would include this little tail, and I'm not including that in my question. I just want to stop here.
Aubrey literally did it, and she got 13.5, and then
I got 81.5, and I don't know.
Okay, so this is our normal model. We're going to make this the standard normal model with the mean of 0, 1 standard deviation above, 2 standard deviations above, and 3 standard deviations above the mean. In the standard normal model, it's just 0, 1, 2, and 3. Those are the z-scores. And -1 standard deviation below, -1 standard deviation, or -2 standard deviations below, and -3 standard deviations below. Now, the area, total area, is equal to 100%. Everything is somewhere under this whole model. The mean is the halfway point. That means half the data is below the mean and half the data is above the mean. They're symmetrical. What's one side is equivalent to the other side. So our empirical rule tells us that 68% of our values lie within 1 standard deviation of the mean. 68% lie within 1 standard deviation of the mean. It tells us that 95%, I'm going to delete this line here. I don't like it. It's not going to let me. Um, 95% of the values lie within 2 standard deviations of the mean. And 99.7, I'm going to put that underneath. 99.7% of the data lies within 3 standard deviations of the mean. So we can use this to estimate certain percentages. Now, if 68% is the middle between 1 and -1 standard deviations, if I divide that in half, on this side, let's get a little highlight our action here. The blue area here has to be 34%, half of the 68%. And this blue area on the other side will also be 34%. Okay, so this section from 1 standard deviation to the mean is 34%, and from the mean to 1 standard deviation is 34%. Now, how do we find the other ones? So, if 68% is in the middle, how much is all the way to the left and to the right? Greater than 1 standard deviation from the mean and less than 1 standard deviation from the mean. Well, everything adds to 100. So 100 minus 68 is 32. That means everything greater than is 16 and 16%. Everything greater than 1 standard deviation, because we're going to divide that 32% into 2 equal parts. So from greater than 1 standard deviation and less than 1 standard deviation, -1 standard deviation, is 16%. And then the middle 95%, I can say from 1 standard deviation, from 2 standard deviations and below, right? I want to know that all the way
100 minus 95 is 5%. Divide that by 2, and we're going to get 2.5%. 2.5% is less than negative 2 standard deviations, and 2.5% is greater than 2 standard deviations. These are all approximate numbers. They're not exact. So can we find this area, what I'm going to highlight here in pink? What is this? Between negative 1 and negative 2 standard deviations, and between 1 and 2 standard deviations. Well, if I know from here all the way forward it's 16, but I want to stop at this line, the 2 standard deviations above that is 2.5, I can subtract 16 minus the 2.5. 16 minus 2.5 gives us 13.5, which means my area in here is 13.5% between negative 2 and negative 1 standard deviations. And then the last little piece is greater than 3 standard deviations. Greater than 3 sigma or less than 3 sigma. Well, 99.7% is between the 3 standard deviations. So we're going to do 100 minus 99.7, which we get 0.3. Divide that by 2, we get 0.15%. So 0.15% of the data is more than 3 standard deviations from the mean. So what is that area between negative 2 and negative 3 standard deviations? Well, we can do that subtraction. We can do 2.5 minus 0.15 gives us 2.35. So this area, let's make this a little smaller so I can come in here. This little red area between 2 and 3 standard deviations is 2.35%. And then greater than 3 is 0.15, less than negative 3 is 0.15 as well. So if we add up all those percents individually as little pieces of the standard normal model, we will get 100%. So you're going to be asked questions about this. So let's clean up this slide a little bit because this is going to be a good reference. Okay, so I'm going to clean this up a little. I'm going to take a picture of it as well so we can reference it again. Right. Many studies on automobile safety suggest that when automobile drivers must make emergency stops, the stopping distances can be modeled by a normal distribution. Suppose that for one model of car traveling at 60 miles per hour, under typical conditions on a dry pavement, the distribution of stopping distances, this is what you need to write down. The distribution of stopping distances is approximately normal with a mean of 165 feet and a standard deviation of 4 feet. What's the stopping distance? What stopping distance is at the 84th percentile of the distribution? Justify your answer. Well, first we need to label our normal model with the means and the standard deviations. So our mean is 165. So 165 goes in the center of our normal model. And then we're going to add 4, 169, 173, 177. And then we're going to subtract 4 3 times. 161, 157, 153. Subtracting 4. So what do we know? We want to know where 85% of this whole model is. Where is 84%? Okay, that's what we're looking for. So what do we know? First thing we know is 84% is more than 50%. So I know it's higher than the mean because the mean is at 50% of the data. And so let's look at our numbers and see when we add them up when we get to 84. So here's our 50 from 0 to the mean. what is the area from the mean to 1 standard deviation? Well, if we look at our picture that we just drew, look in your notes, this is 34%. And when I add 50 and 34%, we get 84%. So the 84th percentile is this number, 169. So if you want to know the percentile, we're going to add up the different percentages that we wrote down on the last slide. Okay, here's another picture. What if you saw the middle 68% here? Middle 68 plus the 16 is going to also give you the 84. I like the idea of knowing that the mean is 50% though, and then you just have to add what's greater than the mean until you get to the percentage you're looking for. Now, we can use the empirical rule to assess normality. Normal distributions provide good models for some distributions of quantitative data. Examples are SAT scores, IQ scores, ACT scores, the highway gas mileage of the 2020 Corvette convertible or any car, weights of a 9-ounce bag of potato chips, heights of 3-year-old girls, heights of 6 months, lengths of 6-month-old babies, or weights of 6-month-old babies, naturally occurring measurements. Some other quantities are more skewed and therefore they're not normal and we can't use the empirical rule for it. If we talk about prices of single-family homes in any city, that's going to be skewed to the right because as you know, you have houses that are about the same range, but then you always have those outliers that are huge and expensive. Survival times of cancer patients after the treatments, it's, you know, you have the data clustered around a lower number and then the rest is kind of skewed to the right the longer they survive. Number of siblings of students in the stats class, also skewed right. It's not that common to have 10 siblings. It's more common to be 1, 2, or 3. And that's normally where you find the bulk of the data, but you also have those outliers. So it's risky to assume that a distribution is approximately normal without first analyzing the data. The first thing we want to look at is the graph. And then we look at the numerical summaries to assess normality. If the graph is clearly skewed, has multiple peaks, or is bell-shaped, that's evidence it's not normal. We don't need to then check the statistics. But if the data is roughly symmetric and bell-shaped, we shouldn't assume it's approximately normal. We can use the empirical rule to give us evidence whether or not it's normal. If about 68% of the data lies within 1 standard deviation of the mean, about 95% within 2 standard deviations of the mean, and 99.7% within 3 standard deviations of the mean, then we can say it's roughly symmetric. We are never exactly symmetric. It's always approximately normal. So it's okay if it's close to these numbers, but not too far off. Let's look at it a little bit clearer. From 87 to 126, that's about here to about here. So how many dots are there? Well, according to this, there are 63 dots out of 77. So that's 81% of the dots, 81% of the serials are within 1 standard deviation of the mean. Now, if I was taking these numbers, I would just be adding 19.484 to these numbers and subtracting 19.484 from that to get this number and this number instead of doing that whole calculation again plus 2 standard deviations. So now our 2 standard deviations, our boundaries are 67.9 and 145.8. So that's going to put us about here and 145 here. That adds 1, 2, 3, 4, 5. See, I'm counting 5 dots here, 6, 7, 8 dots. So that 63 plus 8 gives us 71. 71 dots out of 77, 92.2%. That's closer to the 95 we're looking for, but this 81 is pretty far off with 60 of 68. And then our 3 standard deviations of the mean, again, I would just add 19.48 to this number and subtract 19.48 to the smaller number, We get 48.43 and 165. And that ends up being all of the data. So 100% of the data is within 3 standard deviations of the mean, which is pretty close to 99.7. But because we are pretty far off here, we cannot call this normal because there's too much data between 1 standard deviation of the mean. So, is the amount of cream in Oreo cookies normally distributed? 2 statistics students, Ryan Wells and Ali Quiroz, collected data on the weight of cream in a random sample of 45 double-stuffed Oreo cookies as part of their final project. Here's the data. Here's also a histogram of the data and the summary statistics. So looking at the histogram, that's the first thing we have to see. So right away, the histogram can tell us that it's probably not worth doing the rest of the calculations. So this is pretty unimodal. Well, it's definitely unimodal. And it's roughly symmetric. This one's just a little bit higher than that one. And this one's just a little bit lower than that one. So it's pretty symmetric. We'll test it. What we're going to do is find what are these values? When you're finding 1 standard deviation, 2 standard deviations, you're finding the numbers that we were writing down here on our normal model. You're just not drawing them on the normal model. So we're going to do our mean. It's 6.742. And we're going to subtract the standard deviation, 0.184. And then we'll do 6.742, and then we will add 0.184. When we do that, we get 6.558 and 6.926. So this is 1 sigma, right? This is -1 and this is +1 standard deviation. So that's the first one. We're going to look for this between these two numbers to be 68%. That's the question we're looking for. Then I'm going to subtract 0.184 again. And I'm going to add 0.184 again. I get here 6.374. And then 6.926 plus 0.184, 7.11. We want to know, is this about 95%? That's 2 sigmas. And then we'll add it again. Plus 0.184 and 7.294, that's 3 sigmas above the mean, minus 0.184, 6.374 minus 0.184 is 6.19, minus 3 sigmas. We want to know, is this about 99.7%? Now with a dot plot, we could count the data, right? Because we knew exactly how many dots were at each point, but we can't use a histogram that way because if it's in between, which it is, our lines end up 6.558 is about here. So we don't know how many of those data values are in this bar because we can't see the individual data. So we have to go back to our data set, okay? So we're going to use pink highlighting for numbers that are within 1 standard deviation of the mean. And it's going to start with the first number, the closest number to 6.558. Has to be above it. So 6.52 here, 6.52, 6.55. So here's the first value that is in that interval. So starts here, and then it has to stop at 6.926. So that includes all of these, and it's going to stop at 6.92. Okay, so that's the numbers that are 1 standard deviation either side of the mean. Let's count how many of those there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. So 1 standard deviation from the mean. We have we're going to put that off to the side here, 32 out of the 45 double stuffed Oreos, which is 71.11%. That's not that far off from our 68. 3%. Okay, maybe. Let's look at the rest of them. Our next set is 2 standard deviations from the mean. So I'm going to include anything that is greater than 6.374 and less than 7.11. I'm going to do these in purple. Okay, so it's 6.374. So that doesn't include the 6.37 because that is 6.370. We're not sure if it had decimal places, but we won't include it. And then 7.11, that's including these extras. So let's count how many more those are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now we're going to add 11 to the 32, which gives me 32 plus 11 over 45, which is 43 out of 45. 43 divided by 45 is 95.55. Okay, we're looking pretty good here. That's pretty darn close to 95%. And then the last two, the 3 standard deviations from the mean, that's going to include everything 6.19 and 7.294. So our last value, 7.15 here, that's definitely included. And then let's see, the 6.37 also included. So it adds our last 2 data values in there, which makes it 100% of the data, right? 45 out of 45 are within 3 standard deviations of the mean. So we're really close to those estimates. I think we could say that this is approximately normal. We don't ever want to say it is normal. Nothing's exactly normal. So we're always going to say, yes, it's approximately normal. So yes, the amount of cream in a double stuffed Oreo is approximately normally distributed.